Okay, so that is one thing that we were talking about last time. What I wanted to show you is that I tried to draw some diagram last time, but maybe it didn't go very well. So I drew it later on uh, using my PowerPoint slide, and so this is what I have put here. This is the visual way of looking at that problem. Those of you who couldn't solve it very well, maybe if you look at the same problem in this manner, maybe your thought process may become clearer. So you see what this diagram says is that there is a world of causes. And it so happens that we never know actually what are the underlying causes. We never have a direct contact with the causes. In this case, whether we have the virus or we don't have the virus. All that we have access to is what we can observe, the effect, the test outcome, or whether we have cough or whether we have sore throat and so on. And so most of the time, if you end up catching the disease, then your symptoms will be accordingly present. So if you have the disease, then there is a 95% chance that you have sore throat. Or if you have the disease and if you go and take the test, there is a 95% chance that the test will come out positive. And similarly, if you don't have the disease, there is a 95% chance that you will not be exhibiting the symptoms. But there is a 5% chance that although you don't have the disease, one day suddenly you wake up and you complain of sore throat, maybe because you ate some spicy food the previous night or something. I don't know. Or maybe you have some other thing. Maybe you have just common cold. And because of that, you are having sore throat, but today you think that maybe you have coronavirus, right? So there is a small chance that even if the cause is not present, the symptoms, the effect may still be there, and vice versa. And so what happens most of the time is that we kind of can roughly guess this prevalence about the likelihood of the cause, whether 99% of the population has is virus free or not. Maybe 99% is not the right answer. Maybe it's 92% or 98%. But this exact number, may not matter as much. But we are most of the time able to kind of guess that, okay, this is roughly the ballpark likelihood of whether C is equal to 0 or C equal to 1. So these numbers we probably have. Similarly, we can make a pretty educated guess of what this P error is likely to be. So the numbers that are mentioned here, the probability numbers, we may be able to know that, know them, or we may be able to kind of make an educated guess regarding them. The question is that when we get a particular observation, let us say our test result comes out positive, we have to kind of go backward as shown by these black arrows and then decide the relative likelihood of whether we don't have the disease, C is equal to 0, or whether we have the disease, C is equal to 1. So that is the type of belief updates that we have to do, our brains do. Actually, our brains are very powerful in doing that. Even without thinking too much about it, we kind of come up with at least a rough answer to this type of questions all the time, actually. But if I ask you this a specific problem, then maybe half of you or more than half of you actually got confused and you didn't know how to solve this problem, which is what something that we are going to now be considering in today's lecture. Okay. Oh, and by the way, we saw last time that what this will allow us to do is actually understand that channel capacity equation which you have worked on in your lab, that C is equal to bandwidth times logarithm base 2 of SNR plus 1, right? So that is a very fundamental equation that drives a lot of communication system development in today's world. Okay, for for the 5G and for the 6G. And it is surprising that the reason for that equation, how that equation came about, is something that we are going to be able to appreciate by looking at this type of problem. Okay? So I think it's a very exciting subject to be looking at and to be studying. And the answers that we are going to get are going to put us in a great position to be able to start maybe even contributing in terms of 5G communication systems development. Oh, by the way, I want to mention this to you before we begin today's lecture is that, I was reading an article just yesterday. I wish I had saved it so I could just project it in front of you. That article said that the Chinese president, he has laid out a plan for next 10 years for China. And in that plan, what he wants to do is to put China at the forefront of the technological developments that he thinks are going to drive the world for next 10 years. So he has listed those 10 technological items that he thinks are going to be the most important technological drivers. And he wants to make China equal to, for example, USA or European countries, if not better. And so he is saying that we will devote all our human resources, all our smart people, we will give them a lot of government backing so that China becomes at the forefront of these technologies. And so the 10 technologies that he has listed, what is one of them? It is this 5G communications. And so 5G is where there's a lot of interest, there's a lot of activity, a lot of excitement that is happening. And so if we are focusing on some aspects of 5G, like the one that we looked at in the lab, I think I cannot emphasize enough that it is where the future is. Okay, so now let us begin today's discussion. This is not what I wanted to share. Okay, are you able to see this screen now? The lecture 2 slide?
Yes, sir.
Okay.
Yes, sir.
Okay, fine. So let us start.
Yes, sir.
So now, we have, I think, motivated the need for studying probability, the need for studying estimation, because only by doing so, we are going to be able to answer this problem regarding coronavirus disease or any such problem. But more fundamentally, we were saying that the notion of information, the concept of information can be mathematically answered only in terms of beliefs. And what is the mathematical language that deals with the beliefs? Well, it is ultimately this probability theory. It is the estimation theory. So that is the one that we are going to be looking at. Okay, so today we are going to actually begin by taking a very simple case of these multiple questions that we asked. Remember one of the question was, what is information? How do we generate the information? So, well, we are going to get an answer to that question. And that answer is not going to kind of require us to push ourselves. It's kind of going to fall out pretty easily. You don't have to be mathematically very well equipped to be able to understand the answer of this question about generation of information. But then we are going to look at how the information can be transferred. And what happens if there is some impairment, some noise, some deleterious effects in the process of transferring the information? And in order to answer that question is where we will have to kind of review our concepts of probability theory. So you can almost think of it this like, the initial part of the music, and then the music is going to get a little more intense, where we are going to start looking at the bias theorem. And then we are going to look at something called conditional entropy, and that is going to answer this question of how the information transfer happens. So this, you can almost think of it as some music that is going to start, and the music is going to become more and more richer, so to speak. And you see, it so happens that I mean, a lot of you come from the state of Gujarat, and so you may be doing all this Navaratri, dancing, Garba, and all that, right? So mathematics is sort of like that, when Garba starts, the music is pretty easygoing, pretty easy to jump into. Even if you have some friend from Uttarakhand who has never done Garba, he or she can still join you in that first part of the session. But then the music gets more and more intense. And then you will have to kind of be pushing yourself a little bit. If your friend from Uttarakhand is doing it for the first time, then he or she may not be able to keep up with the steps. And then at the very end, when the music is going like super fast, is when if you don't push yourself, you will be kind of pushed out, right? You will not be part of the circle anymore. But you say that no, I want to get in the game. I have to do this. Then what you will do is you will kind of go on your own. Maybe you will enroll in a Garba class, or you will do the practice yourself. So if you are there all the way till the end, that is where you have the biggest kick, right? When it is like the grand finale, when the loudspeaker is the loudest and the pitch of the music is the fastest, that time if you are still doing Garba, then you get the maximum fun out of it. And so likewise, the initial parts are going to be easy. Probably all of you will be with me. But then you'll have to kind of say that, oh, I have to do this. And you have to do some work on your own to be able to kind of get to part 3 and then part 4. But if you do that, then that is where you're going to get the maximum benefit out of it. And then you will get actually really appreciate the nice intellectual mathematics that will allow us to answer this fundamental question of information generation and information transfer. Okay, so without further delay, let me start. This is the diagram that we had looked at. And so today, what we are going to do is consider only this part of the diagram, which is talking about the information generation, how the information gets generated. Okay, so what we are going to do is kind of to make it mathematically general, we are going to say that information source is going to be modeled as having K symbols. These K symbols are these K circles that I have drawn. These are the K members of a set, the set of information bearing messages. And let us denote them as this set members D1, D2 up to D of K. And this we are going to call it as source alphabet. And so what are some examples? Well, for this problem where we considered the disease being present or not, the source alphabet is binary. It takes only one of two values, whether you have the disease or you don't have the disease. And we denoted the corresponding symbols as being 0 or 1. Right. So this is pretty straightforward. And there are many such type of sources, right? In this case, our body itself is the generator of the information regarding whether we have caught the disease or not. But then many times, like right, if you just toss a coin, whether it comes up head, you can call it as C equal to 0. If it comes up tails, you can call it as C equal to 1. So there is no shortage in coming up with practical information sources which have binary nature, right? And so we are going to be looking at this binary information source a lot, where capital K is just 2. Um, when somebody has in some family there is some birth, then whether the newborn is a boy or a girl is also a big uh, question of interest. And so that also becomes a binary source, boy versus girl, C equal to 0 versus C equal to 1. But then in general, information source is actually most of the time it is not binary. For example, if you're writing in English, then English has an alphabet which is 26 letters. So capital K is 26 for English language. And actually, if you write this sentence in English on your computer on the keyboard, then actually computer uses an alphabet which is even larger. It has total of 128 possibilities. Because on computer you can do many other things. You can put a space in between two letters. You can put the full stop, the period mark, and so on. So this ASCII character set that is typically used has actually 128 symbols, out of which 26 are the actual letters, and then there are a lot of other symbols that are used in this ASCII set. So ASCII is also an alphabet with 128 symbols. Okay, so now we are going to start associating probabilities with these symbols, right? We have already done that for this binary source. Remember that we took the probability that C is equal to 0 to be 0.99, and the probability that somebody picked at random ends up having this coronavirus. We are assuming that it is maybe only 1%. So we are going to assign probabilities to these symbols. For a binary case, it can be 0.99 and 0.01. If you're tossing a coin, it may be just 0.5 and 0.5, right? You have equal chances of whether it comes up heads or tails. For English alphabet, there are some letters we know, like letters such as E, A, I, T, O, like that, which occur far more frequently compared to other letters. For example, Q. When you write a sentence, it is very unlikely that you will end up using Q or X or Z. Even J is surprisingly not a very common letter. If you want to see the probabilities of all the 26 letters of the English alphabet, you can do a search and you will find, for example, this is one website which gives you the frequency or the probability of occurrence of English letters. And so basically, you will have this probabilities associated with each of these symbols. By the way, the index of the symbol is denoted by small k, right? And this capital K here denotes the total number of symbols. So that is something that you want to be clear about. Okay, so we will now right away get into the question of answering how the information can be generated and what are the units of information. And so what Shannon thought about and what he formulated, well, he had actually a detailed reasoning to say this. So we are not going to get into the mathematical aspect of reasoning. Maybe we will do it later on. But today what we are going to look at is something more intuitive. Without getting too much into math, we are going to kind of take like a tip of the iceberg type of answer that Shannon came up with. So what Shannon said is that to be able to define information mathematically, any such definition needs to have two things. Okay. So what are the two things that Shannon said an information definition should have? He said that any definition of information, any formula that pins down the concept of information should make use of P. It should make use of the probability of the occurrence of that kth symbol. And he said something more specific. He said that the notion of information should be inversely proportional to P. Okay, so why is that? So let me give you the answer. You can think about it yourself later on. But intuitive answer of why the information should be inversely proportional to P is that when P is small, we are surprised more, right? So in the coronavirus disease case, we say that C is equal to 1 has a very small probability. And so therefore, if somebody gets the disease, and this is where the notion of utility, remember I mentioned to you, comes into play. If some celebrity catches the disease, maybe 6 months ago, you know, our most famous Hindi movie actor and most of his family got this disease, and that became a big informative event. Why is that? Because we didn't expect them to get the disease, right? So if somebody catches the disease, it becomes a highly informative event because most of the time C is equal to 0. And so C is equal to 1 because it's a low probability event, ends up carrying much more information, right? So this is the reason why information should be inversely proportional to P. If I give you another example, right, something that should drive home the point even more clearly is, let us say that C is equal to 0 means that it doesn't snow in Gandhinagar, and C is equal to 1 is an event that there is a snowfall in Gandhinagar, okay? Now you know that this C is equal to 1 event, its chances of happening are much less than 1%. I mean, you would agree with me that 1% is very high number to assign to C is equal to 1 in this case. They are probably less than 0.00001%, I would think. And so suddenly, suppose if one day you wake up and it is snowing in Gandhinagar, I mean, you will say that, wow, this is pretty informative event that has happened. You will be surprised. And probably all the newspapers, all the TV channels will be talking about it. But C is equal to 0. Do you even think about it? Is there a headline in the newspaper that, okay, today it didn't snow in Gandhinagar? No, because C equal to 0 is, in this case, highly non-informative event. Why? Because this probability is even more closer to 1. And so its inverse is pretty much just equal to 1. It's the lowest value that it can have. When the probability starts becoming closer and closer to 0, that is where the
Sir,
corresponding symbol is going to generate more and more information.
sir,
In terms of English language, therefore, we can say that the letters such as E or A carry much less information compared to letters such as Q, X. So this is one thing that Shannon pointed out.
sir,
Yes?
sir. I have one more example. Suppose
Yeah.
I tell a question that what is the probability of rising sun from east tomorrow? So its probability will be one only. But this information is not too informative. So why it is so?
Right. So when probability is equal to 1, Shannon said that the information becomes 0. And we will see why that is happening. Okay.
Okay.
So the sun rising tomorrow in the morning, that event does not carry any information, like what you pointed out.
And
Okay.
what if we say that the sun will set from east? If its probability is zero, it's confirmed that its probability is zero. So it will
Yes,
be more informative. Means the suppose some unconditional thing happens, then it will be more informative.
correct, correct. So the probability becoming zero is going to be uh, carrying much high information. But you see that for the binary case, there are two possibilities: C is equal to 0 and C is equal to 1. Now, uh, when you associate probability of 1 with C is equal to 0, then at that point, the source stops becoming informative because both C is equal to 0 and C is equal to 1 are determined. Uh, C is equal to 0 is always going to happen, and C is equal to 1 is never going to happen. And so in that case, we don't have any uncertainty about uh, what the source is going to generate. So maybe I should write it here that uh, this here is tied to the notion of uncertainty. This is the notion of uncertainty that we have about what the source is going to generate. If we can know or predict if we can predict what the source is going to do perfectly, then that source stops being informative for us. We don't call that source as informative source. And so we are going to see that the information generating ability of a source is going to be tied to how much we know about the source. You know, we all have relatives, maybe some uncle or some aunt, or maybe uh, a friend of us who is kind of repetitive. You know, he or she keeps on saying the same thing over and over in different ways. And then we say that, well, maybe that source of information is not highly informative. But somebody who keeps on telling us new things every time, uh, we find him or her to be more informative because we don't know what that person is going to come up with next. So that is this item number one that Shannon said. But then the other thing that Shannon said, besides this first requirement, is that the mathematical formula for information should have a logarithmic function. Okay. So why is that? So let us now forget about this P aspect a little bit. So let's not worry about the probabilities, but let us just look at the size of the message set, right? The size we have called it to be capital K. For the binary case, we know that there are two possibilities. Capital K is 2. And so uh, what is log base 2 of K equal to 2? This is equal to
1.
1. And so no wonder that we are using 1 bit here. This C is equal to 0 and C is equal to 1 is just 1 bit. But now let us say that we have some other source for which C takes 4 possibilities. C is equal to 0, 1, 2, and 3. Okay, so how many bits you think we will need to represent this source? We will need 2 bits, right? This will be 0, 0, this will be 0, 1, this will be 1, 0, and 1, 1. Log base 2 of 4. If you have 16 symbols, then we don't need 16 bits, by the way. We need log base 2 of 16, which is 4 bits. And so that is where this requirement came into play, that information should be a logarithmic function. And which type of logarithm it is? Shannon said it doesn't matter. You can use any logarithm you want. But once you use a particular logarithm, the base of that logarithm, in this case, the base is 2. So that will determine the unit of the information. So he actually ended up giving what the information unit should be by this particular requirement. Today, we typically represent information in terms of bits because our computers and our cell phones and our modems, they are designed to deal with switches which are on and off, the transistors and the diodes. They are on and off. And so uh, the computer circuitry is able to deal with binary events very well. And so therefore, the unit of information today is bits. But Shannon said that you can use log base 8 or log base 15 or any other logarithm base of exponent, a natural logarithm. It doesn't matter. But the logarithm function should be there. And yes, if you end up using log base 2, then the unit of information does become bits. So this is the second requirement that Shannon spelled out. By the way, this part you should be now familiar with it. Have you seen
Sir,
this logarithm function anywhere?
Yes, sir. Definitely.
Yes.
Where?
In formula of bit rate.
Exactly. In the formula which defines capacity C. There also we had logarithmic function. So you see that we are starting out, but it is connected to the final answer. By the way, the detailed derivation of final answer probably we are not going to be able to do in this course, but we can see some hints, right, where that answer came from. And then, therefore, Shannon put this 1 and 2 together, and he said that this is how the information should be defined. It should be logarithm base 2 of 1 over pk. This is called I of k, information generated by kth symbol. So this was Shannon's answer. Okay.
sir, sir, I
Yeah.
don't understand the logic behind representing these bits into log to the base 2. So, sir, if we do the log base 2 of 4, then it will be of 2 byte only. And again, if
Two
we do the
bits.
log
Two
of
bits.
2
Two
bits,
bits. There is a difference between bits and bytes.
yeah, bits,
Okay,
yes,
byte is a collection of 8 bits.
yes.
So
So,
here we are talking about just bits.
yeah,
Yeah.
if we do the log again log, if we take the log of 4 again with base 2, it will be
Mhm.
2 bits. And again, then it will be 1 bit. So, how can it is possible to represent the 16 bits into 1 bit?
We can't keep on taking logarithm over and over again, right? Uh, if you have uh, two symbols, let's say here c is equal to 0 and c is equal to 1, you want to separate these two possibilities. You don't want to merge them into one, right? Whether you have the disease and whether you don't have the disease. These are the two possibilities. You want to be not confused whether you have the disease or not. When you tell somebody about this, you say that I don't have the disease. One of your classmates actually got coronavirus, last week, and so he sent me an email and he said that for me c is equal to 1. So if you end up taking log base 2 of this again, then log base 2 of 1 is 0. But then you don't have any bits to deal with. You are merging these two cases into just one possibility. But that is useless. You can't make any use of it. So in order to separate out the different outcomes that the source takes, you have to have those many possibilities. For this source which is generating 16 symbols, you want to be definitely able to separate out this 16 possibilities. And therefore, here I said, oh, by the way, I should have put a vertical marker here. So this is first symbol 0001, and this is the second symbol 0001. And this is the 15th symbol, and this is the 16th symbol. And you don't want to be confused about which symbol the source is selecting. Just the way when you write English, you don't mix up A and B in just one letter. If you end up doing that, then people will be very confused about what you are writing. And so likewise, you can't keep on taking logarithm base 2 of logarithm base 2 of logarithm base 2, because what then you are doing is merging symbols into one another, and then that leaves the discriminability aspect of the source. Okay?
Sir,
So you can take log base 2 only one time, and that I hope it is clear to you why we need to do that. Basically, in order to represent capital K symbols, we need log base 2 of K equal log base 2 of K number of bits. That is where this unit of bits came into play. Okay, somebody else had any question?
yes, sir. Sir,
Yes, go
here
ahead.
we are describing this information in log with base 2 function.
By the
So
way,
it is,
if you have a question, maybe you can just first mention your name and then say the question
yes,
aloud, okay? Yeah, go ahead.
sure. I am Isha Shah,
Okay.
and I have a question that we are describing this information in log with base 2 function. So is it means we can describe by this way only if it is equally likely, like I have 50% probability, then only I can describe this, or
Exactly. That's a very good point. When all of P of K are equal, that is when we can say that this type of bit assignment is ideal. Why is that? We will come to it later on. But when,
okay.
and so that is why when, if I put, for binary case, if I put P of K equal to 0.5, what will be log base 2 of 1 over P of K?
It
It is
is
going to be
1.
1, right? So
Yes.
for the binary case, you will get 1 bit as the answer only if P of 0 and P of 1 are both 0.5. But for
Yes.
coronavirus, you will see that C equal to 0 is going to be very close to 0, because 1 over 0.99 is going to be some number which is pretty close to 1.
Yeah.
And so log base 2 of that number is going to be like maybe 0.001 bit. So this is the amount of information that C equal to 0 generates. Whereas 1 over 0.01, which is 100, if you take log base 2 of this, then you're going to get an answer which is like roughly about 6.5 bits. So what Shannon said is that this unlikely event is going to be far more informative. It is going to carry as many as 6.5 bits of information.
Sir, can bits
Okay.
be in decimal?
Yeah, you can have log base 10 also. Then this will be digits, not bits. The information will become digits in the unit of digits.
Sir, but how can a beats be in a rational number?
Yeah.
That is a very good question. The question is, how can you have 0.001 bit? How can you have 6.5 bits? Bits are
I'm
bits.
asking the same.
They are either zeros or ones. How can you have a fraction of a bit? You can't slice a bit.
Yes.
So that's a very good question. Yeah, I like this question. I won't answer it right now. Okay, but it doesn't mean that I will forget the question. This answering that question is going to take us some time. Okay, so let us move on for this interest of time. These are all nice questions,
Sir,
and it's very good that you all are into that.
sir.
Yes, there is one more question.
Yes, sir. VR Shah. Sir, I wanted to ask that why did Shannon take base 2 only? Was it because of the binary system, or did binary system develop after due to this base 2?
No. So Shannon, actually, while he was much younger, this he did while he was around 30 years of age. when he was much younger. Actually, he was in the college. Okay, he was not maybe much older than you are. Maybe he was 20, 21. He came up with his master's MS or MTech thesis, which was on Boolean algebra. Right? I don't know if you have studied Boolean algebra or not, but it is about logic gates, and it deals with, for example, AND gates, which has two inputs. Both are binary, and its output is one only if both the inputs are one. Similarly, there is an OR gate whose output is
Yes,
one.
sir. There were gates in 12th standard.
Okay, good. So you know about Boolean algebra, you know about logic gates, you know OR gates, AND gates, XOR gates, etc.
Yes, sir.
So Shannon, in his master's thesis, developed the mathematics of this Boolean algebra, and he actually showed how to implement it. And his MTech thesis supervisor, even before Shannon became famous, he said that this was the best ever master's thesis written, right? So Shannon obviously knew about the bits and the logic behind using the bits. But he said that my mathematics is more general. It doesn't have to rely only on bits, but even he said that bits are most likely going to be the currency of computer age. By the way, Shannon is called the father of information age. Before Shannon, maybe 12 or 15 years before Shannon developed his theories, there was a British mathematician called Alan Turing. He is called the father of computer age. And so when Shannon came around, computers were already kind of, at least mathematically, they were well developed by Turing and by others. And so Shannon knew that bits are kind of going to be the currency of computers. And so that was probably the reason why he defined it to be logarithm base 2 as a natural definition of information, but his definition is general enough. Okay, Vihar, so that answers your
Okay,
question?
sir. Yes, sir.
Okay,
Thank you,
good.
sir.
So let us move on. So now we are going to jump into a little bit of probability theory, and we are going to define something called probability mass function, or PMF, which is nothing but all the probabilities collected together, right? So this is the PMF, and you can even draw the PMF on x-axis. You will have symbols k equal to 0 and k equal to 1. This is where you don't have the disease. This is where you have the disease. And the PMF is going to be just numbers, probability numbers. K equal to 0 is going to be very large. It's going to be 0.99. K equal to 1 is going to be pretty small, 0.01. So PMF is nothing but a collection of probabilities of all the symbols generated by the source. And a lot of the times we will draw the PMF in this type of diagrams. Now, this probability mass function has several properties. None of its members are negative. They are always positive numbers. They can be, the smallest value it can have is 0. Those probabilities are never negatives. The second property is that if you sum up all the probability numbers, they have to add up to 1. And the third probability is that if you sum up some ordered set of probabilities, it gives you the total probability of observing an event which is between some Ka to Kb. Okay, so these are some standard rules. By the way, there is another rule which is kind of a derivative of this rule, which says that P of K has to be less than or equal to 1. Okay, so these are some of the rules that you may or may not be familiar with. But this PMF is kind of an important concept. There is another important concept of probability theory that we are going to kind of very heavily be using, and that is this concept of random variables. Okay. So the main point that I want to emphasize, don't get too much into the detailed definition of random variables. The main point is that random variables are numbers. Okay, they are never letters, they are never colors, they are never on-off switches, nothing. Whenever you think of random variables, think of them as numbers. They can be integers, they can be real valued, they can be complex valued, they can be positive, they can be negative, but they are always numbers. And it is these numbers that are probabilistic, and that is why they are called random. So what we are going to do is this symbol generated by our informative source may or may not be enough, right? When somebody has the disease, it's not a number actually, right? But for our benefit, we are going to map that particular source output into a number. And that number is denoted as x of k. So I have x of k for this disease problem was 0 or 1. For English alphabet, for example, if we say A is mapping to 0, B is mapping to 1, C is mapping to 2, and so on, then we will get random variables corresponding to English language. One nice thing that we can do once we convert our source output, we map the output of the source into numbers, the random variables, is that then we can start talking about the expected value or the mean value, which is sort of like the average, and also the variance, which is the square of standard deviation. And those are defined using these two formulas. This is a formula for the expected value, and this is the formula for the variance. I hope that you have studied these formulas earlier, but even if you have not, this is what you take it as kind of given to you. Okay, don't question. This is what it is. Okay, there is one more concept which we are not going to probably be using right away. It will be useful to us later on, but let us just get over with it, which is this notion of CMF, or the cumulative mass function. So again, it's sort of like PMF, but it is defined only for a random variable. And its definition is what is given here. Basically, you do a cumulative addition of probabilities. And so because of that, what happens is that it is always either flat or it goes up. It never decreases. The reason is that as you keep on adding probabilities, the numbers are either going to remain the same. If, for example, some probability is 0, it's going to remain the same, or it's going to increase. But it will never decrease because the probabilities are never negative, right? The other property is that if you go to the very left end of the real valued axis, you will always get a value of 0. If you go to the very right end, it is going to be 1. And then the last thing is that this probability that we were thinking of, what is the probability that certain event happens over certain range, xa to xb? It is a very nice answer. It is just the difference between the CMF corresponding to xb minus CMF corresponding to xa. So CMF and PMF are kind of equivalent. If you have PMF, you can easily calculate CMF using this formula. Or on the other hand, if you have CMF, from that you can also get PMF by just taking consecutive differences. So in general, I already showed you what a PMF chart would look like. A CMF chart would look like this. Okay, it will have because let's say if you're dealing with negative random variables, it will start out being 0, and then it will slowly keep on rising. Sometimes it might become flat, then it will keep on rising, and then it will become 1. So this is 1. So eventually it will reach 1. So this is how the CMF is defined. When you were in your 12th standard and when you were preparing it as a part of a class, you may have seen your performance in an exam in some type of percentile number, right? Maybe your evaluator would have told you that you belong to 95th percentile or you belong to 99th percentile. Well, that is what he was talking about is effectively the CMF. Okay. Now,
Sir,
this
hello.
is where the music becomes little faster. Okay. Now, this is where you will have to kind of step up. You will have to learn maybe a new step here. So far, it wasn't maybe too difficult, although you had some basic questions. But I think those questions, those questions are valid, but hopefully they are not too difficult for you to absorb. Now we are going to kind of increase the pitch. And so now you will have to stay with me. You will have to learn some new steps. Okay? Okay, somebody had a question?
Yes, sir. So,
Yeah.
why those functions are called mass function? What is the meaning of mass in that one? Like CMF and PMF.
Yeah, don't worry too much about those wordings. Sometimes they are just called distribution functions. Okay, probability distribution function, probability or cumulative distribution function. So let's not get too much into that. Uh, there is some detailed mathematics of probability theory which will allow me to answer your question, but I don't want to spend time on it right now.
Okay.
The wording is not important as long as you understand what those PMFs and CMFs mean. That is enough. Later on, we are going to be considering continuous random variables. So far we have considered discrete values. The source takes only finite number of possibilities, total of capital K possibilities. But there are some sources which are continuous. Like when I'm speaking, if somebody records my speech, and actually it is being recorded, and if you plot it as an electric signal, it is going to be continuous. So we haven't considered those continuous valued informative sources. But for such sources, the output is continuous analog in domain instead of digital in domain, discrete in domain. Then this PMF and CMF become PDF and CDF, probability distribution function or probability density function, and cumulative distribution function. And so maybe one answer to your question is that in order to differentiate between discrete valued case and continuous valued case, we are going to be using PMF and CMF for discrete valued case and PDF and CDF for continuous valued case, which we will be studying later on. Okay, so now, so besides defining the information for an individual symbol, which is what this formula is, right? That we looked at, this formula here, which uses logarithm base 2 of the probability, the inverse of probability. What Shannon said is that there is something actually even more fundamental and more representative of the informativeness of the source. And that is the average information generated by the source. Okay. And so he said that we should define the informativeness of the source in an average manner by taking expected value of the information generated by all the symbols. Right? So this is something new. Maybe we can absorb what I of k is individually. But Shannon said that think of those I of k's themselves as random variables. I of k are obviously numbers, right? Because they involve logarithm, and logarithm cannot be used for some things which are not numbers. So obviously I of k are numbers. And we took some examples, right, where I of k was like 6.5 bits and maybe some very close to 0 bits and so on. Shannon said that we should take expected value of all of the I of k's. And that is going to give us the average information generated by the source. And he called it, by the way, the entropy of the source. So now, who can tell me how will I be able to write the equation for h of x? You already saw how to take expectation of a variable. So we are going to be using just the same formula.
Or it will be P of sigma P of k into I of k.
Exactly. Sigma P of k times I of k. But P of k, we have said, is negative log base 2 of P of k. So then this becomes the formula for the average information generated by the source. Right? Okay. So let us take an example. Again, we are going to consider this binary source. It's going to generate x equal to 0 or x equal to 1, head or tails. You have the disease, you don't have the disease, whether it's boy or girl, doesn't matter. But we are going to now associate this number q to this binary source. By the way, it's called Bernoulli source. And it is typically associated with this number q, because q uniquely specifies the PMF of this binary source. In our case, we had taken q equal to 0.01. For boy versus girl situation, it is going to be 0.5, right? So you can now, given this particular PMF, you can obviously calculate the expected value. And if you do the math, which is already given to you here, it turns out that the expected value of this source is equal to q, right? You can also do the calculation of variance, which I suggest that you do it on your own. And you should get an answer which is given here. Okay, information of individual source. So it is going to be obviously negative log base 2 of q and negative log base 2 of 1 minus q. And then finally, the entropy is going to be given by this formula over here. Okay, so this is an example for a binary source of several quantities that we have mathematically defined so far. Now, let us actually experiment with this. Okay, so I'm going to see. I'm going to share my MATLAB window. Let me know if you see it or not. Okay. Okay, are you able to see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so I wrote this MATLAB program, and let us run through it. Okay. This is not the one that I wanted to show. This comes later. This is the one. So this here is going to be our experiment with entropy function. So, okay, so let me see. So I defined this entropy function. Right? So this is the entropy function. What it takes is the PMF vector as the input, and it does that calculation which I just showed to you. You are able to see this for the part which I'm highlighting?
Yes, sir.
Okay. Okay. So this is what this function does, right? So whenever you see this entropy function, inside of this entropy is this calculation which is going on, which we just looked at. And so here I'm going to run this entropy for different values of q. And this slider is going to allow me to control the value of q. So right now q is set to 0.53. If I run it, then you see that entropy comes out to be 0.9974. And remember, this is in terms of bits. Why? Because inside the entropy function, I use log base 2. If I had used log base 10, then it will be in terms of digits. Right now, this is in terms of bits. So now what we want to do is slide this and see what is going on.
Sir, what is meaning of entropy, sir? Here?
Sorry?
What is meaning of entropy here?
It is the average informativeness of the source. It is the average value of information generated by the source.
So how the
Right? That is
formula
what
is
we just looked at.
how the formula
Sorry?
is derived for it? How the formula for entropy is derived then?
We just went over it. Right? It is the expected value of I of k. You want me to go back to that?
Yes, sir, little bit.
This is what we just now went over, that entropy is going to be the average informativeness of the source, which is the average value of individual information values. And the average is going to be calculated using expectation, which has this formula. And this is the formula that I had programmed in that MATLAB function.
Okay.
Make sense?
Yes, sir.
So now let me go back to so what I'm doing now is I'm changing Q, right? So you will see that as I reduce Q, the entropy keeps on going down. If I make Q equal to 0.01, okay, at 0, let's not worry about it, but at 0.01, the entropy is pretty small. 0.01 is only 0.0808. So our coronavirus situation has a pretty low entropy. Why is that? Because although it's pretty worrisome disease, most of the time people don't have this disease, still even now. But if suppose the situation became worse and more people started getting it, then when it will become most informative is when P starts becoming close to 1, close to 0.5, sorry. So when I make this Q equal to 0.5, entropy becomes 1. So from 0 to 0.5 value of Q, entropy went up going, entropy kept on going up. If I increase Q further, then funny thing is going to happen. Entropy is going to go down. Right? And so as I bring this closer and closer to 1, it's going to become smaller and smaller. And so in terms of what we have said earlier on, this is not surprising. When Q is equal to close to 1, 0.98, what it means is that most of us has coronavirus. And so that time, again, there is not much information if somebody takes, if you know that somebody has the disease or not. So what Shannon said is that the informativeness is the highest when you least can predict. Your prediction ability is the least, which is what happens when Q is equal to 0.5. When you toss the coin, that is where you have the greatest uncertainty. Remember, that is what I said earlier, that information is going to measure the uncertainty we have in what the source is going to do. And so that is why entropy is taking its highest value of 1 when Q is equal to 0.5. Okay, so now this part of the code is where I have actually calculated the entropy values, where I took all the values of Q from 0 to 1 in steps of 0.001. And then I put that in a for loop, and I calculate entropy for each value of Q. I store it in this vector, and then I just over here, I'm plotting them. So if I do that, then I get this result. It's like a parabola. So you see at q equal to 0 or 1, by the way, I don't know why this is written as 1, it should be q. X-axis title is wrong. But so x-axis is q and y-axis is entropy, and it is becoming highest. It is taking the maximum value when q is equal to 0.5, right? So this is how the entropy looks like for binary variable, Bernoulli variable. Okay, so now maybe the last thing that we will do today is evaluate the entropy for a known binary source. And here I'm taking capital K equal to B4. And now what I'm going to assume is that the PMF has this particular formulation. The first symbol will have a probability of 1 minus q, and then the remaining 3 symbols will have share the remaining probability equally. So they will all be q divided by 3. And if you add these 4 values, you will notice that this becomes 1, right? The sum of the last 3 values is q. If you add q to 1 minus q, you get 1. Do you understand why now my PMF is having 4 elements? Yes or no?
Yes, sir.
Yeah.
Yes. And this is very specialized PMF, okay? For a binary source, this is the only way to define the PMF, q and 1 minus q. There is no other way. When it is non-binary source, you can define PMF in many ways, many different ways. This is just one way that I have used so that I can still control the PMF using this q parameter. So now again, I'm going to do the same thing. I'm going to see what the entropy turns out to be. So you see when q is equal to 0.74, or actually let me make it exactly equal to 0.75. That is when the entropy becomes 2 bits. When q is equal to 0.75, what is going to happen to PMF?
All
All
will
will
be
be
equal.
same.
All of them are going to be equal to 1 over 4, which means that all 4 symbols are equally likely. And therefore, the entropy is going to be just log base 2 of 4, which is 2. But if I reduce the value of q, then it is going to decrease because now the source probabilities are not going to be uniform. So the values are going to become lesser than 2. And it doesn't matter, even if I increase beyond 0.75, then also it will decrease. So to see this again in the graphical manner, I redid the same thing. I have put this in a for loop, and I'm generating the entropy of a quaternary random variable. And you see that it gets maximized when q is equal to 0.75. For other values, the entropy is smaller. Okay, so I will be giving you this program and I will ask you to take it to the next level by experimenting. Okay, and what you can do is some suggestions I have given here, but you can actually come up with your own experiments. Okay, so let me end over here. And before I stop, let me see if any of you have any questions.